Hello calculus student, this video is for 4.10 derivative, antiderivative, part 2. So in the first part we talk about the notation of and also what's the process of finding antiderivative, which is reversing derivative, and also the symbol for it, which is the indefinite integral notation, integral f of x dx. And we introduced the power rule, so we're gonna do two more. Okay, so there's a lot of these. Other than the power rule, most of these are just matching the differential and integral tables. So look at this: 4 integral 4 over 1 plus x squared dx. So 4 is a constant multiple, we can move it out. And so basically we have to do 1 over 1 plus x squared dx. Is it a power rule thing? No, it's a 1 plus something. Do you recognize that when you do a derivative of something is 1 plus x squared? What was it? Look at it. Oh, when you do at the bottom, when you do arctangent, it was 1 over 1 plus x squared. So if you see any of this answer here, then you know that. So you see how you do integral of 1 plus x squared, it would be arctangent x plus c. So basically that's how you do it. So we'll say, oh, there's no rule for it. You just have to know it. You have to memorize it back and forth. So this is actually for arctangent x plus c, and that's it. Okay, it's easy. When it is open book, open notes, it's a little harder because you have to memorize a lot of stuff. What about integral tangent x cosine x? You would say, well, it looks a lot familiar. Remember something tangent x something? But oh gosh, it is secant x tangent x, not cosine x tangent x. So I don't really have anything that matches it. Okay, so integral is very specific. You have to be in this form and then have this answer. Okay, so what should we do? We can use trig identity to simplify it. Maybe it's something that you can do after you simplify it. So what is tangent x? Is sine x over cosine x. And then we have to multiply cosine x, right? This cancel. So that is actually dx, okay? That's actually sine x dx. Can I do sine x dx? Yes, there is a function. When you do a derivative, is equal to sine x. That is cosine x. But when you do derivative of cosine x, it was negative. So you have to start with negative plus c. So look at the table. You do anti-derivative of sine x is negative cosine x. Okay. So the last part of 4.10 is something called the initial value problem. So it is actually to find the real f of x, that is the antiderivative of f of x. If we know some point of the big f of x, the one that you have not done derivative on. So, and we call this kind of problem initial value problem, because very often the value that you give for the big f of x is an initial value, like when x is 0, what it is. So then you can use it to solve for c. So to solve for c, so you no longer if you do plus c, you actually know what c is. So it is called initial value problem. And then we have different notation for doing it. So we'll talk about it in the first example. And for work problems, so you can also remember if you have a position function, you do a derivative, right? d dt. You would have velocity, right? Velocity is s prime. And then you do a d dt again. This is change of velocity, is acceleration. So now, in the initial value problem for this kind of question, you will be given a of t, and then you can do integral dt to get back to velocity, and then do the integral dt, we call it integral dt, we get back to the position. Okay, so this is a work problem related to motion problem. So let's do a problems related to just a generic function, a generic antiderivative initial value problem. Now for initial value problem, we do not use big f of x. We would actually use f of x for the one that we want to find. And then the derivative, which is the original f of x, is called dy dx. So they would use the old notation. F of x is here. You do the derivative of it. You do a derivative. You have dy dx. So you are trying to find what this is. So this is not f of x. Okay, whereas in the antiderivative notation, we have big F of x, right? And you do a derivative, it is f of x, right? This is the derivative d dx, and this is integral. And then you do the integral, you get it back. So integral and d dx. But in solving initial value problem, we never use the big F of x. Okay, this is not the notation that we use. We do this. We say f, whenever you see f of x, it was the original one. So we'll say dy dx equal to 2x. Find the original one so that 0, 1 is on f of x. So I know some point here before the derivative. So this is an example of an initial value problem. So you would say f of x is what? F of x is equal to the integral of dy dx. So integral of 2x dx. That's how we write it because this was the original. Yeah, so the notation switch. And then so how do I do this? This is just an antiderivative problem. It's 2. And then x squared over 2, right? x1, x squared over 2. So cancel out plus c. So my f of x is actually x squared plus c. But I have an initial value of 0, 1. So, and then I would want to solve for c. To solve for c, plug in 0, 1. So 1 is 0 square over, no, over 2. 0 square plus c. Oh, c is 1. So actually so my f of x now I can actually write it as x squared plus 1. And this is the answer. I solve an initial value problem. Basically, it's doing an integral. Basically doing integral of a one that has the derivative or is undergone in the derivative, and then solve for c. Okay, whenever it is initial value problem, you solve for c. The motion problem. So remember we say if we have v of t, we can go back and by doing integral, and then if we have a of t, we can go back to. So like if I have a of t, I can do an integral. Okay, dt. It would give me v of t. And then if I do an integral dt, it would give me s of t. Because in the past, I do it derivative. Okay, so I have a car traveling at the rate of 88 feet per second at time equal to 0. And then the brake is applied at 15 feet per second square. So this is deceleration. So deceleration. So a of t is negative 15. The brake applied, that means it's deceleration. Find the velocity. If you know a of t is negative 15, you do an integral, you have v of t. So you will say v of t equal to integral negative 15 dt. It's a constant, right? So you just say negative 15. So this will be negative 15t plus c. But I don't know what c is. Oh, I know at t equals 0, v is 88. So solve it. So it'll be 88 on this side equal to negative 15 times 0 plus c. Oh, actually c is 88. So my v of t would actually equal to negative 15t plus 88. And that's the answer for v of t. Okay, you plug in to solve for c. What is the position function? That's s of t. How do I get s of t? I integral v of t. So I'll do it here. So you would say s of t is equal to position, right? Integral v of t dt. So negative 15t plus 88 dt. So these are just power rule. So it will be negative 15t squared over 2 plus 88t plus c. Again, I need to solve for the constant. Oh, but my s of 0 equals 0, so 0 equals 0 plus c. So c is actually 0. So this one is the precision function, just this, because it's 0. How many seconds before the car stops? So whenever the car stops, you would know that v of t is equal to 0, solve, right? So my v of t, is negative 15t plus 88 equal to, right? So that's equal to 0. So that means 15t equal to 88. T is equal to 88 over 15. Approximately 88 over 15, 5.87. So if you apply a brake like that, that would take that much longer to actually stop. So how much does it travel? So how much does it travel means would be the position of it after, because the acceleration is constant, there's no going back and forth. So you know that you can just do s of t and plug it in. So s of t is what? Negative 15t squared over 2 plus 88t. And this is the time when it stops. So it would be negative 15 over 2 times 5.87 squared plus 88, 5.87. So that would be, let's put in the calculator, negative 15 over 2. Oops. Negative 15 over 2 times 5.87. Oh, this one is a square. Plus 88 times 5.87. Some rounding error because I didn't use the real one. So it has traveled 258.13 feet. So that's why people say if you are traveling 88 feet per second is about, like, I think 60 miles per hour. If you press the brake, it travel around 200 feet. You still have some time before you can brake. Okay, so that's the end of 4.10.